Okay, since the number of students will be fixed today, I will be arranging the classrooms today or tomorrow morning. I will let you know through the LMS or the Piazza, probably through both of them. We will probably not be in this classroom. Most likely, if they are free, we will be in one of the P1, P2, or one of those classes, because there are approximately 40 students. A bit less, I mean, this morning there were a bit less than 40 students who were interested in taking the midterm. So we don't need such a large amphi. The material will be everything that we have done, including today. I mean, for any midterm, any exam that you will take from me, I mean, this year, next semester, or through your education career, the answer to the question, what will be the subjects in the midterm, the answer will always be the same. Anything we have done until the midterm. Any other questions about the midterm? It will be around 4 or 5 questions, 3 hours, with some bonus. I will let you know when I arrange the classroom, because I don't know. There are several large classes in this university, like this General Physics 1, and unless there is one this weekend, we will be in one of the P1s, P3s at 9:30. But if there is one, I don't know where I will arrange. I will just try to find a suitable hour and place. Any questions about the things we have done on Tuesday? Remember, we started studying fluid dynamics. We started with some simple stuff. We had mainly dealt with the pressure, what we mean by pressure, what is the definition of pressure, how we can calculate the pressure, and then we had some applications of the pressure, like the buoyancy. Why does objects float on the liquids? And we calculated that, for example, a typical aquarium does need to support hundreds of kilos, a large one. And then we discussed the buoyancy, why do objects float, how does the ships work. Did anybody go to the civil engineering department to see the boat made of concrete? Well, we had some architects in the classroom, even they didn't go apparently. Okay, so today there will be mainly, I will try to cover 2 subjects. One is the hydraulics. So if you are driving a car, and unless you are driving a car from the 60s, did anybody drive a car from the 60s or even from the 80s? So you drove, well, okay, so you are quite familiar with the cars. So if you have driven a car from the 80s, one of my father-in-law has a car from the 80s, and it is as good as a gym, going to the gym, because your muscles have to work a lot. So you are doing the actual muscle work to rotate the wheels in the car. But in the newer cars, you can just rotate the wheels with just the tip of your finger. It's so easy to rotate them. And the reason is the hydraulic system. So apparently the basic idea, we had already covered the basic idea. We had seen that the pressure in a fluid is always the pressure at some reference point plus the density of the liquid times the gravitational acceleration times the difference in the heights of your reference point and the point at which you are calculating the pressure. And it is actually the height. These 2 points can be completely at different points. They don't have to be on the same horizontal position. One can be here, the other can be right over there, because we had already seen several things. So if you had imagined such a system, and it is filled with liquid, this is your liquid system. And if you would like to, let's just assume that they are at the same height. They will be at the same height in equilibrium. Now, if you take this point and this point, let's call this point A, this point B, and consider the points on the opposite side. Let us call this point C and this point D. The differences in the heights of the point C and D and A and B, they are let's just assume they are equal. This is H, and this is also H. They are equal. The differences in the heights are the same. Now, so we know that the pressure at the point A, minus the pressure at the point B, remember the differences in the pressure at two different points is always given by the H, the differences in the heights. So this difference is equal to the pressure at the point C minus the pressure at the point D. Since the difference in the heights of this point and this point is the same as the difference in the height of this point and this point, so PA minus PB is equal to PC minus PD. The pressure differences are the same. But we also know one more thing. Remember, you can just imagine this block of liquid. I'll just imagine this is a horizontal line. Just imagine that the bottom part of this liquid is also horizontal. So this block of liquid is horizontal. It is not moving in the horizontal direction. So the force at this point and the force at that point should be equal. But that means the pressure at this point and the pressure at this point, the other point, has to be equal. So we also know that pressure at the point B should be equal to the pressure at the point D. B and D, they have to be equal. So we know that from this equation tells us that the pressure at the point A and the pressure at the point C are also equal. Well, what we are essentially doing is to show such an identity. You just start from the point A, you imagine such a block, and relate the pressure at the point A to the pressure at the point B, and then you use this block of water to relate the pressure at the point B to the pressure at the point D, and then you use the last block of water to relate the pressure at the point D to the pressure at the point C. So as long as 2 points are connected by some water, so as long as you can swim from one point to the other point through the water, it just means that the pressure differences is only determined by the differences in the H. One point can be here, the other point can be over there. There's no problem with that. Okay, that although it seems kind of obvious, it will have important consequences. So let's just take this example. So you have a small opening and a large opening. They are both connected by a fluid. So you imagine that you have a piston over here and another piston at the same height. So they are both at the same height. It is filled with liquid. And let's say you apply some force over here. And let's just imagine that the force that you exert on the other one, you exert another force on the other side, and let's just assume that these two forces are balanced. So the system is at rest when you exert a force Fa on the left-hand side and you exert a force Fb on the right-hand side. Now remember, the pressure at any point is always P0, the reference pressure, plus rho g h. Now in this case, h is 0. So we will just set this point to have h equal to 0. So this term is 0. So the pressure at that point is just the reference pressure. The reference pressure, we have the atmospheric pressure. So this is the additional force that we are exerting. There is the atmospheric pressure, which will exert some force, plus we are pushing it down by some additional force, Fa. The same holds over here. There is the atmospheric pressure plus this additional force, Fb. Now, Fa will increase the pressure over here by FA over A1. Let's just call it the area 1. Okay, this has area A1, and this piston has area A2. So this is the system we have. So if you imagine this system, now FA over A1 will be the increase in the pressure of this point, right below this piston. But if the system is balanced, everything is at rest, the liquid is at rest. Now if the liquid is at rest, the pressure at this point and the pressure at this point should always be the same. If we are increasing the pressure over here by applying a force Fa, that increases the pressure here. If we want to balance the forces, we should also be applying some additional force Fb to keep the system at rest. And the force that we should apply over here, Fb, should be such that the increase in the pressure on this side and the increase in the pressure on the other side, they should also be equal, because the pressures at this point and at the other point should always be equal. This is Fb over A2. So if the system is at rest, even if we apply some external forces, then the external forces should always be related by this relation. So you can imagine that on this side you put a car, or a large, or it can be the brakes, a heavy load, the brakes in your car, or the steering system in your car. There is a force that you should exert on something else. If you are holding a car over there, you should be exerting some normal force. This piston should be exerting a normal force on the car so that the car will stay at rest. But in that means the car is exerting a force on this platform equal to its weight. Now, if we want to keep the system is at rest, we should exert some force over here, Fa, and Fa and Fb should be related in this form. So this, you can imagine, is your load, and this is the force that you exert. So the force that you need to exert, Fa, should be equal to A1 over A2 times Fb. This is the force you need to exert. Now, the Fb is your load. There might be several different loads. That's not something that you can really control, but when you are devising such a system, A1 and A2 are the things that you can control. And you might make sure that A1 over A2, A1 is a small area, A2 is a large area. You can construct your system in such a way such that the force that you need to apply to balance an object can be much smaller than its weight. Now this is the critical thing over here. So it might be that here you have, let's say, an object that is 100 kilos. You need 1,000 Newton to balance it. If the ratio of these areas is 1 to 100, if you just put 1 kilo over here and 100 kilos over there, they will just balance each other. So it is just a lever system. If you remember, in the lever system also, if you have one side is very long, the other side is very short, a very small force on the long side, you can lift a very heavy load in the short side. This is just exactly the same system. You have a short side and a long side. Of course, if you want to lift the car by, 10 meters, just imagine you have this system. So you have this system filled with liquid. You have a pistons on top. This area is A1, this area is A2, and A1 over A2 is equal to 1 over 100. Let's just imagine. Now, in this case, if you put a load, M2 is equal to 100 kilograms, and here you put another load, M1 is equal to 1 kilogram, 1 kilogram, the weight of 1 kilogram will balance the weight of 100 kilogram in this case. But there is a price you pay. If you want to lift the second mass by 1 meter, you have to push this first mass 100 meters. You are exerting a smaller force, but you have to displace it much further if you want to create some displacement on the large mass. It is just the conservation of the work, the conservation of energy. The work that you do here and the work that is done here, they should be equal. If you are exerting a force that is 1/100th of the other force, then the displacement you need is 100 times more. Okay, any questions on this one? Now, this subject I would like to pass fast, because there is another subject which I would like to cover, which is more interesting and a bit more complicated. This one. Then this will move by 100 meters. Yes. Now, up to now, we have always dealt with liquids at rest, or almost at rest. So in this case, if you are pushing this, of course, the liquid is not at rest, but it is moving very slowly. Now we will start the subject, what happens if the fluids are not at rest? Now, in this sense, is air a fluid or a gas? In some aspects, it's a gas. In some aspects, it behaves like a fluid. So let's first discuss the fluid aspects. Ooh. Okay, so let's see how is my internet connection. Okay, so this is one idea. This is a model for an airplane. No, you cannot see it. Well, this is a model for an airplane wing. Well, you see, just a test trial, let's say. So okay, just note this part. What they are doing here is that from these points, there is the air flowing from the right to the left. At these points, they just release some gas. And you see that for most of the cases, the gas just flows parallel. They do not mix. This is what we call the laminar flow. The fluid, or in this case, the gas, just flows as if it is made up of layers, and each layer is flowing independently without mixing the other layers. Now, if you look at over here, there is some very slight mixing between different layers. So you see there is this layer coming and hitting the wing. It is no longer a layer. This part is a bit curved, so it just curves a bit up. This one comes as a layer, but it just spreads, and here you cannot really say that it is a layer now. But now this is when the wing is horizontal. Now at this point, you can no longer claim that it is a layer by layer flow. This is what we call the turbulence. It's a turbulent flow at the side. And you see that the turbulence is affected by the shape of the wing and the angle with which the wing is staying with respect to the flow. I think this is something around the 60s or so. So they just try different shapes of wings and to see how does this turbulence change. And this is more or less a typical modern day wing. Okay, so here there is some turbulence. Mainly it is a laminar flow, but if you compare it with this one, you get lots of turbulence over here. This is when it is horizontal, it will be changing its orientation. Now you see there's still more or less, this part is a laminar flow. And on the bottom, the flow is almost always a laminar flow. The turbulence doesn't start from here. Doesn't start yet at the bottom. And you see that on the top, these layers are being squeezed together. The separation between the layers of the, let's go back. Anyway, I think you saw it. Okay, this one. So you see, the layers at the top have been squeezed. If you look at the separation between the layers here have this spacing more or less, but here they are squeezed together. So the cross-sectional area through which the layers move is smaller. Now we will see now that this just means that the layers are moving with a faster speed. The speed at the top is more than the speed at the bottom of the layer, of the foil. Now this is one question that we would like to analyze. Another thing we would like to analyze is this one. Now this is kind of a short video. Okay, so just look at the trajectory. I think he will do it again. So it doesn't go through a line. So up to now, we have always seen that if there is no force acting on an object, it should go through a line. So this is definitely not going through a line. So it starts here, it moves in that direction. So will he repeat it? Okay, so you see, it started here, it started moving in this direction, but then it hits this point. So this is where it hits. So it started here, went towards the left, but it hit the right point. So it is definitely not going along a line in the horizontal direction. In the vertical direction, we don't expect it to go on a line. It should follow a parabola, but in the horizontal line, it should follow a straight line, horizontal plane, because there is no force acting on it in the horizontal plane. But it definitely doesn't do so. So there should be some force acting on it. And that is what we will be, that's another thing that we will be studying it. The planes, why the planes fly, and this one, they almost have the same physics. So let's see. Now, first let's start, what is laminar flow? We had seen an example of a laminar flow versus the turbulent flow. I'm not sure that this is the right way to spell it, but so for those who have taken an airplane, so is there anyone of you who didn't take an airplane yet? Okay, are you afraid of flying? Well, I am. But there are some moments while you are flying that the plane just falls. I mean, as you are flying, you are flying smoothly. Suddenly, it is as if the plane is making some free fall downward. It falls like a few meters. That is also called by turbulence, because while there is a laminar flow, there is a lift. There is a force pushing the airplane upwards. But when there is a turbulence in the air or caused by the plane, that force drops significantly and you start dropping until you leave the region where the turbulence is. And you might have also realized that the turbulence happens most frequently when there are clouds around, because the clouds will modify the homogeneity of the atmosphere in that region, and that usually causes the turbulence as you are moving. The properties of the atmosphere around you is changing, so the force acting on you is changing. So that's why you get all these turbulence and you just jump up and down. Now, what we will be studying mainly is the laminar flow. That is the easiest one. The turbulent flow, I don't know if we really understand it completely. It's the fluid dynamic is a complicated problem. And well, do you think that the weather forecast, they can forecast the weather precisely? Yes or no? Well, that's a problem in fluid dynamics, almost fluid dynamics. The atmosphere behaves like a fluid in most cases. Well, the weather forecast, since my childhood, they have improved significantly, because now we have much larger computers also, that you can reliably predict how the weather will be tomorrow or the day after, but in 1 week time it's completely unreliable. The reason is that it is also kind of there are turbulent flows which we cannot predict. Now, what we mean by laminar flow in a fluid is that we had just seen an example, and the gases, the smoke, they were just flowing along one line, and they were not mixing together. So if there is one line like this, the other line does not intersect the previous one. That is what we call the laminar flow. They don't have to be parallel. You can have flows like, if you look at on a river that is flowing smoothly, the river might take curves. Well, that is still a laminar flow. You might see eddy small waters that curl around some point. That is turbulent flow. Now, in that mini scales, let's say, the river might be flowing smoothly on the large scale, but on the mini scale, especially close to the shores, you will see these whirling parts of the liquid a lot. On the small scale, it's hard to make predictions, but on the large scale, you know that if you just put some piece of wood on one part of the river, if you know how fast the river is flowing, you can determine where it will be. But if you just put a very small dust speck on one part, it will be almost impossible to predict where will it be in some other time. Now let's just take about the laminar flow. If you just put some fluid over there, it will just flow smoothly to some other point. If you put some other object over here, it will flow smoothly. It will not intersect the first one. Or you put another object over here, it might flow smoothly and come over there. Another object, it might flow smoothly and come over here. So if you just imagine that you started from this line, you might end up having your objects lying on this line. The area might change. You see, you might put objects very close to each other, covering almost an area in the fluid. And as the fluid moves, those objects can move away from each other, and the area might enlarge if the flow is in this direction. Let's say the flow is in this direction. This is the direction of the motion of your objects. Now here, the fluid might have some velocity, some speed v1, and on the other side, it might have some speed v2. The speed of the liquid need not be the same throughout the fluid. Now the area here is, let's call it A1, and the area on the other side is A2. Now just imagine a very small amount of time. So in this very small amount of time, what will happen is this area, if you just put some specs over here, it will just move a very small distance. So it will come to this point. And this is the volume over there. Now the length, let's call it L1, is nothing but V1 times dt in a very small amount of time. Now if you consider the other side, this side will move in this direction, and the thickness of that side will be just V2 times dt in the same amount of time. So this part moves over here, this part moves over there. But the mass, so let's see, if you just take this area, this volume, now the mass that comes in should be equal to the mass that goes out. We are of course assuming that the amount, well, since these lines cannot disappear, they cannot cross each other, the mass here should be always constant. So the mass inside has been increased by this, by the mass over here, and it has been decreased by the mass over here. If there's mass accumulation, then the question is for how long will the mass accumulate? If the mass is constantly increasing over there, eventually you will have all the mass of the universe inside. Or if the mass is decreasing in time, well, that means eventually there will be no mass over there, but we are assuming that the flow is stationary in the sense that it is not changing in time. So the total amount of mass inside this volume should be the same. But it just tells me that if the density over here is ρ1, the density over here is ρ2. Now ρ1 times A1 times L1. A1 times L1 is the volume over here. The volume times the density is the mass. So this is the mass over here, the mass that enters into this region. And the mass that leaves that region is ρ2, A2, L2. So these two things have to be equal. This is what we call the continuity. Well, L1 is V1 dt, L2 is, this is L2, V2 dt. So this means that ρ1, A1, V1 should be equal to ρ2, A2, V2. This should hold as long as the liquid is flowing in a stationary state. The liquid is not changing in time. There is no accumulation of mass at any point. So here we have already assumed that the mass inside that volume is not changing. So we are assuming that there's no mass is accumulating in that region. So the mass that comes into that region should be equal to the mass that goes out of the region. So this is what we have. ρ1 A1 V1 is equal to ρ2 A2 V2. Now, if you are talking about a gas, the density of the gas can be changing from point to point. The variations in the density of the gas can be significant. So ρ1 and ρ2 can be really different. But for a liquid, ρ1 and ρ2 are more or less the same. So we can just assume that ρ1 is equal to ρ2. Now, if the densities are the same, it just means that you cannot really compress the liquid. This is what we are assuming. So we are assuming that the system is an incompressible liquid. Well, any object is compressible to some extent. But in this case, we are just ignoring it. Compressible, we are meaning that if you take some mass of an object, you can change its volume without changing the mass. So you can change the density for any object by just exerting some additional pressure. You can squeeze objects. If you squeeze the objects, you are increasing the density. But if ρ1 is equal to ρ2, that is, if we are in the incompressible region, this means that A1 V1 is equal to A2 V2. But if you have seen a river, you have probably witnessed this one already. So you see, if there's a region where the river is very narrow, the water will be flowing very fast. It will be flowing very fast because in that region, the area will be small, so the velocity has to increase compared to some other area where the river might be, if it goes through a narrow region over here, it will be flowing very fast. When it comes to a wider region, it will be flowing very slowly. So as the area increases, the speed should decrease. That is why the plateaus are forming. When the rivers go to the seaside, fall onto the sea, effectively the area is almost increasing indefinitely. So the water just becomes very slow. But if the water is very slow, it cannot carry all the mass that it has been carrying when it had a larger velocity. So all the mass that it had gained while it was flowing very fast is deposited in the openings to the sea. And then by just accumulation of all these mass, you get the formation of the deltas. Question? Yes, exactly. Because when you are squeezing the mouth of it, you are lowering the area. Now you are not, so just imagine that this is your water hose. The water has some velocity and some area over here in this part, so you are not changing that. So what you are doing is you are just squeezing the tip. If you squeeze the tip, well, let's see, A1 V1 is just constant. You are reducing A2 by squeezing the tip. So V2 has to increase. So the water jet should exit the water hose with a larger speed. If it has a larger speed, it should go a farther distance. It's exactly that one. Okay, yes. Here I have ρ1 A1 V1 is equal to ρ2 A2 V2. This is the general thing. But if we assume, well, this is what we have. If we assume that the liquid is incompressible, we cannot squeeze the liquid. Under that assumption, this will hold. Well, for water, when you are squeezing the tip of the hose, you cannot really compress the water. You don't exert enough pressure to compress the water, so this will hold to a large accuracy. This one. Now, because L1 is equal to V1 dt, L2 is equal to V2 dt. Well, that color is hard to see. L1 is equal to V1 dt, L2 is equal to V2 dt. So I'm just assuming that I absorb my liquid for a very small amount of time. So all this volume over here Now, in a very small amount of time, all this volume over here will enter this region, and all the liquid in this volume will exit the same region. So here I just assume that the mass of this region is constant during this process. Since I'm assuming that everything flows in a stationary state, nothing changes in time. Of course, the water flows, but when I look at the water, I see the same thing now, I see the same thing 5 minutes from now. So the amount of mass in this region should be the same. That is my assumption. That is the system I'm studying. So the mass entering this region and the mass exiting that region, they should be equal. It is this expression. But this is in a time dt. I divide both sides by the same time dt. So this is what I have. Yes? Exactly, that's the point. I'm just saying that rho 1 times, this is the equality of the masses. Rho 1 and rho 2 can be equal. That means if the masses are equal, the mass that comes in and the mass that goes out are equal, and if the densities are equal, that means the volumes of the two, this one, the volume that enters into this region and the volume that leaves that region, they should be equal. Well, the volume is A1, L1. So A1, the area here times this side, L1, should be equal to the area here, A2 times L2. So that means A1, V1 is A2, V2. Any other question? Now, in the next hour, we will be studying the Bernoulli's principle. So have some coffee.